Wonderful. Okay, it's 8:30 already. I'd like to welcome Rowan Rowlands. He's going to be talking about CAT0 cubical complexes and their connections to flag simplicial complexes. Please take it away.
Right, thank you. Yeah, thanks for the introduction. Thanks to the organizers for letting me speak. Yeah, so I'm currently at the University of Washington in the US, but before I was here, I lived in Canberra. So yeah, it's great to be at least kind of virtually back in Australia for a bit. All right, so let me tell you about CAT0 cubical complexes and flag simplicial complexes. So let's start off by defining some of the words in this title. Right, so if you caught the last talk in this room, then you've already seen about simplicial complexes, but just in case you missed that talk, let me define them again. So a simplicial complex, there's actually two different perspectives I want to talk about today. So first off, there's the abstract perspective on a simplicial complex, which is a collection of sets with this property here. So this property says that for every set in our collection, then every subset of that set must also be in the collection as well. So it's kind of closed undertaking subsets. And here is an example of a simplicial complex. I'm kind of using the shorthand notation for sets. So for example, this doesn't mean 12, it means the set containing 1 and 2. But yeah, here is a list of sets. You can check that it satisfies this condition. All right, so that's the abstract perspective on simplicial complexes. I think there's a slightly more enlightening viewpoint of simplicial complexes, which is the geometric perspective. So to convert between these perspectives, every simplicial complex has something called a geometric realization, which is an arrangement of simplices in Euclidean space with one I-dimensional simplex for each set in a simplicial complex of size I+1. Okay, so let's start off with what is a simplex, or simplices for plural. So a simplex is, well, it's the convex whole of affinely independent points in Euclidean space, but for today's purposes, what you need to know is a zero-dimensional simplex is a point, a one-dimensional simplex is a line segment, a 2D simplex is a triangle, three-dimensional simplex is a tetrahedron, and then there's some higher dimensional ones as well, but they're hard to draw. So yeah, for today, this is all you need to know about simplices. And so let's take a look at our example simplicial complex and construct its geometric realization just to see how that looks. Okay, so we start off with an empty set that corresponds to the empty simplex. I won't draw it because it's empty. Then we've got some sets of size 1, which should correspond to zero-dimensional simplices. So those are the points. So we'll draw some points, label them 1, 2, 3, and 4. And then we have some sets of size 2. So they correspond to one-dimensional simplices, which are line segments or edges. So I'll draw an edge between 1 and 2, and 1 and 3, 2, 3, 2, 4, and 3, 4. And then lastly, we have these sets of size 3, which correspond to two-dimensional simplices or triangles. So I'll fill in this triangle between vertices 1, 2, and 3, and between 2, 3, and 4. Okay, so that's the geometric realization of this simplicial complex. Now, yeah, hopefully you can believe me in when I say that these two different perspectives, this kind of list of sets and this picture, kind of capture the same information as each other. So we often think of this picture as being the simplicial complex. And actually, from this perspective, this lets us talk about other kinds of complexes built of shapes that aren't necessarily simplices. So for example, we have cubical complexes. So today I'll define a cubical complex as being an arrangement of cubes instead of simplices in Euclidean space, satisfying a couple of properties. Before we get to those, when I say a cube, what I mean is a hypercube of a non-negative dimension. So that means the Cartesian product of the line segment 0, 1 to the d. This is not necessarily three-dimensional cubes, they can have any dimension. Okay, and then the two properties that a cubical complex should satisfy. First up, for every cube or in the simplicial complex, then every face of that cube should also be in the simplicial complex. This should remind you of the subset condition for simplicial complexes on the previous slide. Also, when I say a face, I mean a vertex or an edge or a two-dimensional face or a three-dimensional face. This is, again, a catch-all word for faces of all dimensions. And then the second condition here just guarantees that the cubes kind of glue together nicely. So any two cubes in the cubical complex should have an intersection that's either empty, so they don't touch each other at all, or they intersect along a common face of those two cubes. All right, and here are some examples of cubical complexes. There's a three-dimensional one here, a two-dimensional one here. One-dimensional cubical complexes are also called graphs. And here's a cubical complex with some components of different dimensions. We call this a three-dimensional complex because there is a three-dimensional bit, but yeah, the cubes don't all have to be the same dimension. All right. So we've defined simplicial complexes and cubical complexes. So those are the nouns in the top title. Let's take a look at the adjectives. So first up, we have flag simplicial complexes. Luckily, this one's pretty easy to define. A simplicial complex is called flag if you can build it by looking at its graph, finding every clique in the graph, so that's every complete subgraph, and then turning that into a face of the simplicial complex. So for example, this complex on the right here is not flag because these three vertices here form a K3 in the graph of the simplicial complex, but they don't form the vertex set of a face of the simplicial complex. Right, so yeah, flag simplicial complexes, you can build them from their graphs by including every possible face, in other words. Okay, next up we have CAT0 cubical complexes. This is slightly harder to define, but let's give it a go. So we say a cubical complex is CAT0 if, first of all, it needs to be simply connected. That's a topological condition that yeah, basically says it doesn't have any holes, or it doesn't have any one-dimensional holes in some sense. And then the second condition says that the link of every vertex is a flag simplicial complex. Okay, what is the link of a vertex? Roughly speaking, a link of a vertex is what you get if you take a tiny sphere centered around that vertex and intersect it with a complex. So for example, in this first picture here, if I draw a tiny sphere around this highlighted vertex like that, then intersect that with the complex, then you get, you kind of get a triangle like this. Or well, you get the boundary of a triangle, but not the interior of that triangle. And so this simplicial complex is not flag, and so the cubical complex is not CAT0. But you can check for all the vertices in these other two pictures, then the links are flag simplicial complexes, and so these two are CAT0. All right, so this is the definition we're going to use today, but I'll just make a historical note that, that the reason these things were first studied was from a metric space perspective. So the definition that, that was first used was this one that I'm calling a theorem here. Yeah, it was Gromov who first proved that they were equivalents. This other condition says that a cubical complex is CAT0 if and only if it still needs to be simply connected. And also it has non-positive curvature at every point, whatever that means. I'm not going to get into that because yeah, I'm a combinatorialist, not a metric space person. But yeah, historically, the reason these were studied was because they give good examples of metric spaces with some nice property. They've also been studied through connections to group theory as well. There's also a couple of applications to, they show up in phylogenetic networks, and they can be used to, yeah, they come up as some kind of configuration space of a discrete robotic system in some sense. So yeah, a couple of nice applications, but I am interested in them because they have some nice combinatorics. All right, so in particular, I care about finite cubical complexes, and kind of the state of the research into finite CAT0 cubical complexes. There hasn't been very much research into them so far. Probably the biggest theorem is a theorem by Ardila et al., which I will tell you in a minute, but before I can tell you that, I need to give one more definition. Okay, so let's define something called a poset with inconsistent pairs, or a PIP for short. This is a poset with one extra relation on it, which we call an inconsistency relation, which satisfies a couple of properties. I've listed them here for completeness, but you don't really need to worry about what they are for today. There's just a poset with one extra relation on it. I will point out the first condition says that, that the relation is symmetric, but other than that, yeah, don't worry about what the properties are. All right, then this theorem by Ardila et al., that's Federico Ardila, Megan Owen, and Seth Sullivan from 2012. they constructed a really nice bijection between cosets with inconsistent pairs and rooted CAT0 cubical complexes. Right, so a cubical complex is called rooted if it's a cubical complex, but one of the vertices is called the root of the cubical complex. So it's really just a cubical complex, but one vertex has a special name. So you can kind of just ignore the word rooted. Excuse me. All right. So this bijection that they construct is, yeah, really nice combinatorial bijection. There's a very concrete relationship between these two things. But yeah, that was kind of the state of research into CAT0 cubical complexes when I started on this project. Oh, wow, losing my voice. Sorry about that. Okay. So yeah, now that I've told you how things stood when I started work on this, let me tell you about some of my contributions. So let's start with one more definition. We're going to define something called hyperplanes. Unfortunately, these are not the same things as hyperplanes in affine space that you might be familiar with, but this is a very standard word for cubical complexes, so we're kind of stuck with it. But so yeah, if you know what a hyperplane is, forget that, this is something different. So a hyperplane, let's start off with hyperplanes in a cube. If we think of that cube as being, yeah, this kind of standard embedding of 0, 1 to the d, then the ith hyperplane is the subspace you get when you set one of the variables or the ith variable equal to 1/2. Like kind of taking the cube and slicing it in half in one of the directions perpendicular to a basis vector. So for example, a two-dimensional cube or a square has two hyperplanes. There's this vertical one, this horizontal one, or this three-dimensional cube has three hyperplanes, and so on. Okay, then those are hyperplanes in a cube, but for hyperplanes in a cubical complex, what those are is, well, you just take the hyperplanes of the individual cubes and then glue them together where they kind of join along a common face. So for example, in this cubical complex on the left, here is one of the hyperplanes, this kind of horizontal line here, or there's a vertical hyperplane here. There are, I think, 6 hyperplanes in total in this cubical complex. For the one on the right, there's a hyperplane that kind of crosses through it like that, or there's one that's kind of a horizontal slice that goes through like that. I think that one has 5 hyperplanes. Yeah. Okay, so those are hyperplanes in a cubical complex. Now, let me introduce the main construction for this talk. It's something called a crossing complex. We're going to start with a CAT0 cubical complex and then build a simplicial complex out of it. The way we'll do that is that the vertices for this simplicial complex will be the hyperplanes of the cubical complex. And so once we define the vertices, next we have to define what the faces of the simplicial complex are. So to check whether some set of hyperplanes forms a face or not, what we need to do is check if the intersection of those hyperplanes in the set is non-empty. So let's take a look at an example. If we start with this cubical complex here, for example, the set 1, 2, 3 forms the face of the crossing complex because the hyperplanes 1 and 2 and 3 all have, they intersect in a common point in the middle of this three-dimensional cube here. Or for example, 2, 4 is a face because hyperplanes 2 and 4 intersect at this point here, and so on. Okay, and yeah, I claim that this crossing complex, this simplicial complex, captures a lot of the combinatorial information from the CAT0 cubical complex that you build it from. So for the rest of this talk, I will try to convince you of that claim. So let's start with a couple of the basic facts about crossing complexes. So first up, this first lemma says that, that this idea of looking at the intersection pattern of hyperplanes is not completely original. If you look at the graph of intersections of hyperplanes, so you look at whether pairs of hyperplanes intersect rather than arbitrary sets, then what you get something that was called the crossing graph, which was studied by Mark Hagen and a couple of other people. And so my contribution here is to not just look at the graph or the like network information here, but look at the higher dimensional structure as well. So yeah, like in the previous talk, the difference between like this network perspective or yeah, hypergraphs and simplicial complexes, to look at the higher dimensional structure as well. Okay, then this second lemma on this page, I'm also attributing it to Hagen because it's essentially Hagen's observations, but phrased in simplicial complex language. So the crossing complex is not just any simplicial complex. It turns out that it will always be a flag simplicial complex. So yeah, that's the connection between flag and cubical and CAT0 cubical complexes from the title of the talk. But flagness is the only restriction on crossing complexes. Any flag simplicial complex does appear as the crossing complex of some CAT0 cubical thing. Okay, and then finally, this lemma here addresses this theorem by Ardila et al. Remember, they gave a construction between CAT0 cubical complexes and posets with inconsistent pairs. So in theory, there should be a way of building the crossing complex from some cubical complex by looking at the PIP instead of that cubical complex. And this lemma says, yes, you can do that. The way you do that is that the faces of the crossing complex are the consistent antichains of a PIP. Okay, so an antichain in a poset is some set of elements that are all incomparable, and then it's called consistent if no two elements are inconsistent by this extra inconsistency relation. But yeah, there is a concrete way of building the crossing complex directly from this PIP. Right. Here are a couple of more facts about crossing complexes. A lot of the words on this slide might be unfamiliar to you, but I'm kind of throwing them out there just to demonstrate some of the connections between these two things. So the crossing complex is pure if and only if the cubical complex you build it from is also pure. The crossing complex is connected as a topological space if and only if the cubical complex doesn't have any cut vertices. And the crossing complex is something called balanced if and only if the cubical complex is also balanced in a cubical sense. Okay, since I know there are a lot of graph theorists at this conference, I'll mention that balanced has something to do with graph colorings. So a simplicial complex is essentially it's balanced if the chromatic number of its graph equals the clique number, more or less. So yeah, connections to graph theory there. Okay, then there is one more fact about the crossing complex that I am particularly pleased about. Before I can tell you that fact, though, I need to give you one last definition, and that is for the F polynomial of a complex. So the F polynomial is the polynomial where the coefficients of that polynomial count the numbers of I-dimensional faces of that complex. Now there is a detail about conventions here that I'm sweeping under the rug, but anyway, let's get into this lemma. This lemma says that there's a very strong connection between the F polynomial for the cubical complex and for its crossing complex. And what you do is to construct the F polynomial for the cubical complex, you take the F polynomial for the crossing complex, but replace the variable t with t plus 1, then you just get the F polynomial for the cubical complex. A very neat result or neat connection between these two complexes. Now, the reason I like this lemma so much is because of this corollary here. Remember I said that every flag simplicial complex appears as the crossing complex of something. And as a result of that, this relationship between the F polynomials actually gives us a bijection between the sets of F polynomials of CAT0 cubical things and of flag simplicial things. All right, so yeah, in my kind of area of research, the problem of characterizing the set of F polynomials of some kind of complex is a very popular kind of problem to study. And some types of complexes, the set of F polynomials is very well understood, and some types it's not well understood at all. And to the best of my knowledge, this set is one of the sets that's not very well understood. So this theorem here doesn't like completely characterize it, but it does introduce a whole new world with which we can try to study this set. So now we can use tools from metric space theory and poset theory to try to study these sets. All right. So yeah, that was the result I was hoping to tell you about. Yeah, thank you for your attention.
Okay, let's all give Rowan a round of applause. Great talk. Okay, does anyone have any questions for the speaker?
I have one.
Mhm.
So what can F polynomials do, and is it easy to find them? Because I am new to the language.
Okay. So the F polynomial is probably the more familiar perspective on those is for F vectors, which is just the vector where the entries are the numbers of I-dimensional faces. Yeah, so a lot of work has been done into trying to characterize what kinds of vectors can show up for different kinds of complexes there. There's a certain linear transformation you can do to these F vectors to turn them into something called an H vector, which is also something people want to study. It has a lot of connections to ring theory, actually. So given a simplicial complex, there's some kind of ring associated to it. And then if the complex is nice enough, then you can recover the H vector from some algebraic properties of that ring. And so, yeah, ring theorists care about that a bit. Yeah, those are the things that come to mind. I'm sure there's many others, but yeah.
Thanks, Rowan.
Does anyone have any other questions?
Oh, sorry.
G Wang, you have a question?
Yeah, I have a question. So the crossing complex or complex is like a duality?
Not entirely. So I do think that yeah, there's a very strong connection between the crossing complex and the cubical complex, but it's not a bijection. There's a surjection from CAT0 cubical things to flag simplicial things, but in general, there can be many cubical complexes that have the same crossing complex. So yeah, for duality, I'd kind of hope that there'd be some kind of reverse direction, but there isn't. So kind of like a weak version of duality.
Yeah, okay, I see. Thank you very much.
Along those same lines, do you have any, can you give is it possible to draw a quick example of two cubical complexes that have the same crossing complex? Or
sure, yeah.
Yeah, do you have any idea of how you might characterize when two different cubical complexes give you the same crossing complex?
Oh, characterizing in general, yeah, I think that would be a hard problem, but I can give you,
fair enough, but
yeah, I can give you some examples. In fact, there's a pretty big class of examples. So one-dimensional cubical complexes are the same thing as graphs, and then it is CAT0 if and only if it is a tree. So yeah, any tree is a CAT0 thing, and the crossing complex of a tree is just a bunch of isolated points. Number of points here is number of edges in the tree, and so any two trees with the same number of edges will have the same crossing complex.
Okay. And there aren't any higher, are there higher dimensional examples where I have cubes or 4 cubes and all that too? Okay.
Yes, yeah. So for example, here's one. Okay, that's okay, badly drawn. Let me try again. So this one has the same crossing complex as, this might be slightly hard to draw as well. This complex here, I believe.
Okay.
Yeah, there's plenty of examples.
Gotcha. Okay, yeah, thank you.
Maybe one thing I could add there is, if the crossing complex is a connected manifold, then I can prove that there is a unique cubical complex for that crossing complex. But yeah, other than that, yeah, there's often many cubical complexes with the same crossing complex.
Can your manifold have boundary?
Sorry, without boundary. Yeah.
Okay. I had a kind of an additional question to that. So I can imagine for general cubical complexes, you can get some pretty awful gluing, things back into each other. And so it may be difficult to tell, like I can imagine for a non-CAT0 complex, it's very easy. It might be difficult to determine whether or not the cut hyperplane complex, what's the name of these things?
Crossing complex.
The crossing complex, yes. Has more than one element or not. Is that easier with CAT0 complexes? Like, is the fact that you don't have holes and they have to have like negative curvature, like keep you from like horribly nesting on each other?
So yeah, in general, yeah, hyperplanes can do really weird things in general. Like they can intersect themselves. They can, like two hyperplanes can intersect in more than one place. Yeah, just really weird stuff happens in general. I think the reason why CAT0 things work so nicely is, okay, part of this theorem by Ardila et al., or at least part of that paper, was that they gave a way to embed any CAT0 cubical complex into a cube in kind of a standard way. And if you look at cubical complexes that embed into cubes, then the hyperplanes behave a lot more nicely there. There's still some weird things that can happen, but they work a lot better than the general case. And so I think it's that property that makes CAT0 things so nice.
Okay, I have one more question, which I was really hoping to ask. So in the case that the flag simplicial complexes are actually polytopes, can you say anything nice about the cubical complexes or like the crossing complex that corresponds to that?
Yeah, so I think I mentioned in answer to one of the other questions that if the crossing complex is a manifold without boundary, then there's a unique CAT0 thing associated to it. So yeah, polytopes are spheres, well, boundaries are spheres. So, so yeah, then there is a unique cubical complex. Yeah, this kind of unique cubical complex looks kind of like a simplicial cone, but for cubes. So there's a special vertex that's contained in every facet. So kind of like, yeah, that's the analogous property to cones in the simplicial world.
So then is there like it's like a corresponding like toric variety that you can construct through these things? Is what you're saying?
I know basically nothing about toric varieties, so I don't think I can answer that question. I know there's some connection between cubes and toric varieties. Yeah, I don't think I can say anything. Sorry.
Yeah. Okay. Well, thank you for that. Does anyone have any additional questions for the speaker? Okay. If not, let's thank Rowan again.